Welcome back to the course on fluorescence spectroscopy, principles and applications. If any of you have looked at any of the previous lectures, I hope you found them informative. Today we're going to start our discussion about quenching. It's a really very wide field and it could cover multiple lectures. And for the moment, we're going to divide things up into two lectures, maybe even a third one later on. Today we're going to talk about the very basic aspects of fluorescence quenching, which are static and dynamic quenchings, which have sort of two different origins. We're going to explain the meaning of the static and the dynamic quenching constants. It's very important to understand what they mean. Providing examples of these processes and providing some effects that are frequently observed that confuse the analysis. In the future lectures, we'll be talking about quenching in membranes and surface effects and other more complicated phenomena. So let's look at some quenching in the real world. It's always my favorite to use the gin and tonic example. So here we have an example of tonic water with a UV laser diode there. Obviously a modern experiment because some years ago this would have taken a very expensive laser to do. And in this solution there is no added sodium chloride, which happens to be a quencher of quinine, and here we have some sodium chloride added to it, and the sample is quenched. I've told this story before, but I always like to tell it. This was used as an excuse by the settlers in Africa who found that tonic helped prevent malaria. So that allowed them to contact the old country and have the old country send them some tonic water and probably some gin with it as well. So what is quenching? Quenching is really any process that decreases the intensity of the fluorescence. So let's say we have a protein and it has a fluorescent residue on the surface. In case of a protein, it would be a tryptophan. In the absence of quencher, it would have a higher intensity than in the presence of quencher. Or if you looked at the intensity versus quencher concentration, the intensity would continue to go down. In this particular case, I just used the example of tryptophan and schematically tried to show you what two cuvettes would look like rather than two samples of quinine. There's two main types of quenching. There's dynamic quenching and there's static quenching. We're going to talk about dynamic quenching first. And this is a type of quenching where the fluorophore and the quencher, they're both diffusing freely in solution. They have some collisional rate, and when they do contact one another, the fluorescence is lost. The complex, if it is a permanent complex, usually it isn't. If it is a permanent complex, returns to the ground state with no emission. Static quenching is different because it depends on a binding affinity between the fluorophore and the quencher. And this is an affinity that persists even after the sample has been absorbed some light and there's no emission from this complex. So this is going to be a case where the fluorophore and the quencher have some natural affinity for one another. So let's look at dynamic quenching in a little bit more detail. As usual, we'll use the Jablonski diagram as our guide. As I said at the beginning, it's useful for everything. So anyway, the light absorption occurs instantaneously. The fluorophore goes to the excited state. It can now have a choice of what to do. It can either return to the ground state by radiative decay or by non-radiative decay. And those two decay constant, that determines the quantum yield, the fraction of the light that radiates relative to the total fraction of the light will give you the initial quantum yield. Alternatively, a 1 over those two ray constants gives you the lifetime of the fluorophore. In the case of dynamic quenching, we've given the fluorophore another pathway to the ground state, but it's a pathway to the ground state that doesn't result in any emission. So that particular fluorophore is just quenched. And so what happens, this decreases both the intensity and the lifetime. Now this is going to be our standard equation, which is the Stern-Volmer equation, which is the most important one. But you can derive that from yourself by taking the ratio of the initial fluorescence to the fluorescence in the presence of the quencher, where you see we've added the quenching rate here, or you can take it from the lifetimes where we've added the quenching rate as decreasing the lifetime of the excited state. But taking either of these ratios will give you the Stern-Volmer quenching constant for collisional quenching. The usual way of presenting quenching data is by the Stern-Volmer equation. If you didn't use the Stern-Volmer equation for collisional quenching or any other type, basically as the quencher concentration increased, you would see the fluorescence intensity decrease. We put it as a ratio here so we could just start it at some value and it drops down. So the intensity over the initial intensity becomes smaller. The lifetime of the initial lifetime becomes smaller. And that's one way of examining the data. The standard way of examining the data is to take advantage of the Stern-Volmer equation, in which we use the value of F naught or F, and we plot that instead of the initial intensity, and we plot that versus quencher concentration. That becomes a linear plot, which for the older guys like me, we always like to have a linear plot. A characteristic of dynamic quenching is that the decrease in intensity is always equal to the relative decrease in the lifetime, or conversely, in Stern-Volmer terms, F naught on F is always equal to tau naught on tau. And that's basically a proof that the quenching is a dynamic process due to collisions in solution. Static quenching is different. You can still use the Stern-Volmer equation, and I'll show you a little later, but in any event, the form of the equation is exactly the same. F naught on F is equal to some constant times the quencher concentration. So if you look at the fluorescence intensity versus the quencher concentration, it goes down, and F naught on F would go down also. But if you look at the lifetimes, tau naught on tau, you find it stays perfectly equal to 1. The lifetime doesn't change. And that's because when you have static quenching, some of the fluorophore is tied up, being bound to the quencher. The quencher is non-fluorescent, and since it's non-fluorescent, you can't observe it. So the only thing you can observe is the free fluorophore in solution, whose intensity goes down, but the lifetime remains exactly the same. So I wanted to emphasize that dynamic and static quenching had the same functional form. What might you expect in these cases if you didn't have some additional information? Well, since dynamic quenching depends on diffusion, you expect there to be more dynamic quenching at higher concentration. Since static quenching depends on binding between the fluorophore and the quencher, that's thermodynamically driven, and you would expect the higher temperature would break that complex apart, at least partially. So as you notice in these two plots, we've wrote the tau naught over tau as 1, because the only thing that is being observed is the free fluorophore in this process. How to visualize this? I like to visualize it as follows. In the case of static quenching, you actually have, it's not really a rate process, but you have a phenomena which is tying up some of the free fluorophore, and that results in what actually is quenching, but it's not due to dynamic quenching. So the static quenching removes some fraction of the fluorophores from the observable population. In the case of dynamic quenching, the quenching is due to collisions with the quencher, which shorten the fluorescence lifetime. And of course, the diffusion rates are increased at higher temperatures. Here is one example, one of my favorite examples, which is the proof of dynamic quenching by lifetimes. Here we used oxygen quenching of tryptophan, and what we found in this case is that the tau naught on tau values are precisely equal to the F naught on F values, which proves collisional quenching. So let's, if I'm not mistaken, the next slide allows us to interpret these quenching constants. This one's a little bit difficult to explain, but we have two factors that are determining the amounts of quenching. We have the what we're going to call the bimolecular quenching constant and the fluorescence lifetime. Both are contained in the dynamic quenching constant. So naturally, if the lifetime is longer, it gives you more time for fluorophore quencher collisions to occur, and you expect to be more there to be more quenching, and that's what's always observed. The information that is used mostly from these experiments is the bimolecular quenching constant, and that's because it contains information on the rate of diffusion of the fluorophore, in the case of membranes, on the local concentration of the quencher, and it depends on the collisional rate. So I've written a few of these down here. In addition to diffusion, it would depend on the flexibilities of proteins and membranes. As we've found in many experiments, proteins are highly permeable to oxygen, and it might reveal something about the effect of ligand binding on protein dynamics. So there's information to be had in the bimolecular quenching constant, And in order to understand that, we have to consider what is the collisional rate of a fluorophore with a quencher in a fluid solution. So under typical conditions, and this is from physical chemistry, so you have to go back to your physical chemistry books to derive this completely, but the collisional rate is given by some constants, which is really going to become equivalent to a volume around which there is quenching, and the product, and here we use the sum of the radii of the quencher and the fluorophore, both for the fluorophore and for the quencher. So we need to know these numbers. Where do we get these diffusion coefficients from? Well, they're taken from the Stokes-Einstein equation, which is a general equation that will provide the diffusion constant, which depends on the temperature, and of course it goes down with radius. So we can get a diffusion constant, and if we use values typical of small molecules in water, we find that there is a maximum rate. And I know the units might seem a little confusing for the moment, but you'll see they cancel out in further calculations. The maximum value that is possible for diffusion-controlled reactions in water is 1 times 10 to the 10th reciprocal molar reciprocal seconds. That is that, but actually the quenching rate includes another factor. It turns out oxygen is 100% efficient in quenching, but there are many times where the quenching is not completely efficient. So the fluorophore can contact the quencher, and it is not necessarily returned to the ground state. So we say that instead of this calculated bimolecular quenching constant, the maximal bimolecular quenching constant, the one that we observe is that maximal value times some, whatever the quenching efficiency happens to be. So I gave you an example of that in comparison these two slides. The previous one we just looked at, if you use here's an experiment you can do at home. You can use the data on the graph, use the known lifetime of tryptophan, and calculate the bimolecular quenching constant, and it comes in to be this value of 1 times 10 to the 10th. Let's look at the data for indole. If we use the slope of this curve for indole, we get a certain quenching constant, which we don't know if static or dynamic, but since the lifetimes and the intensities, the ratios go down the same way, we know it's dynamic. I didn't happen to have the lifetime of indole around, but I know it was close to 5 nanoseconds. And from this, we calculate the bimolecular constant. Quenching constant is 0.66 times 10 to the 10th reciprocal molar reciprocal seconds. So that could mean one of two things, and this experiment does not tell us which. It could be that iodide is a less efficient quencher, so this apparent value is lower. I don't think that's the case from lots of other experiments that have been done, but its most likely cause is that iodide being an ionic species, is tied up to some extent with the water, and that slows down the diffusion coefficient below the value you observe for a non-polar water molecule in aqueous solution. So let's take an example of this. And this is almost a counterintuitive example, because what you expect if a ligand is binding to a protein, you expect the whole system to become more rigid in some way. Well, anyway, this is the cyclic AMP receptor from some microorganism, I believe, has 2 tryptophanes per subunit. This a protein affects a lot of things in cells: gene expression, the use of energy, cell division. So it's a pretty central receptor. In the absence of CMP, we notice the quenching curve is showing downward curvature. We're going to show in a few slides later that this tells you the accessibility of the 2 tryptophanes is not the same. If we have cyclic AMP in the sample, we see a linear Stern-Volmer plot, which indicates that all the residues are quenched the same way. So in this case, the ligand binding causes some conformational change in the protein, which exposes the second tryptophan for more quenching. And okay, we'll come to that. The type of quenching depends on what the state of the molecule is in solution. So we have here imidazole and imidazolium, which happens to be a quencher of tryptophan. Indole, which is this part of the tryptophan molecule, is known to be an electron donor. The imidazolium is much more electron deficient than the imidazole. So as a result, the imidazole is a very weak quencher, and the imidazolium is a very powerful quencher for tryptophan or for indole. Static quenching. So let's talk about static quenching, where no emission is observed, and after the molecules might remain complex, maybe they'll break apart sometimes, just because unless it's an extremely strong reaction, the reaction would be breaking apart and rebinding. So what's our model for static quenching? Well, the Stern-Volmer graph is sort of changed because we have the molecule going to the first excited state from which it can emit, or by a collision with a static quenching molecule, it forms a complex which can not emit. So only the free fluorophores are observed in this case, and the lifetime is not changed because the only molecules you're observing are the uncomplexed molecules. Initially, we derived the Stern-Volmer equation based on using the Oblonsky diagram, but it can be done in a slightly more rigorous way. For those of you who are mathematically inclined, we can consider the equilibrium constant for binding of the fluorophore and the quencher. We have to consider the conservation of mass, which is the total amount of fluorophore is equal to the free fluorophore and the bound fluorophore. We rewrite the association constant using that conservation of mass, and then it's really quite simple. We multiply by Q, and we get something that looks like the Stern-Volmer equation, and by simple rearrangement, it is the Stern-Volmer equation for static quenching. So from first principles, you can get the static Stern-Volmer quenching constant. Examples of static quenching are somewhat hard to find in the case of small molecules. In the case of larger molecules, it's easier, but this has always been such a powerful example that I've used it. It's the quenching of tryptophan by a protection group that is used in peptide synthesis. And if we look at the intensity, it goes down. If we look at the lifetime, it remains completely the same. So that tells us it's static quenching. But we could have figured that out even without doing the lifetime measurements, because if we assume a lifetime of 3 nanoseconds, which is approximately right for tryptophan, this gives us a static quenching constant of 10,000 reciprocal molar, and the apparent quenching constant is 3 times 10 to the 13th. So this is simply too large for diffusion controlled quenching, so there has to be some binding between the molecules because they couldn't collide with one another fast enough for that to occur. This example is less obvious, but this is caffeine, which we're all exposed to, which is able to quench the single tryptophan in serum albumin. And so we can look at that data. The stacking of this electron diffusion caffeine on the electron rich indole is what the static process is. Calculate the Stern-Volmer quenching constant, calculate the bimolecular quenching constant, and you find it's 100-fold over the diffusion controlled limit. So once again, you know it cannot be collisional quenching because it's too fast, and it's almost a charge, certainly a charge transfer interaction between these two groups that cause the quenching, which means at the time of excitation, a caffeine molecule is already stacked onto the tryptophan residue in the protein. That's immediately deactivated and removed from the what can be observed. So what are some typical examples of dynamic and static quenchers? If you just looked at the types of molecules, you can almost guess. Oxygen, we already said, was a dynamic quencher. Acrylamide is nitrogen oxide. These are small molecules, and they're dynamic quenchers. When you get to larger molecules like nicotinamide or nitrogenous bases, they have a higher tendency to become static quenchers. Now let's get to something that's a little more complicated. What happens when you have both static and dynamic quenching going on at the same time? And that can occur. What does it look like? If both static and dynamic quenching are occurring at the same time, you will observe an upward curving plot for the ratio of the intensities, F0 over F, versus quencher concentration. But if you measured the lifetimes instead, it would be a straight line. This is because there's two processes contributing to the quenching, and they can be accounted for by the simple product of the terms for the dynamic quenching and the term for the static quenching. So this is the expression that we use to explain when both processes are going on. I'm an old timer, so this was before computers. instead of using a computer analysis, we would make the process linear. So you take the combined effect, break up the terms, move them around, and what you do is you define an apparent quenching constant, which is what you have at any point on this curve, and you find out that it's equal to the sum of the two quenching constants and a term that contains the product of the two quenching constants plus the quencher concentration. So if you plot the apparent quenching constant versus the reciprocal of the quencher concentration, you get a linear plot. And we've done that for this case. This is the combined quenching caused by guanosine monophosphate of 10-methyl-acridinium chloride. So this is the structure for 10-methyl-acridinium chloride. The intensity quenching is obviously higher than the static part of the quenching. You could divide up those terms if you wish, but that's not necessary. But what we do with this type of data is we make a plot where, since the apparent quenching constant has only linear terms in it, we can use the slope and the intercept. So we plot the apparent quenching constant versus the quencher concentration, and we get a slope that equals the product of the two, and we get an intercept which equals the sum of the two, and obviously with these two you can separate them apart and separate the dynamic and the static quenching components for this particular case. That all sounds simple, and it pretty much is, but there is a couple of caveats, and we'll discuss some more in the next lecture. But one is that close fluorophore quencher proximity can look like static quenching. In this very extreme example, we consider that we have an acceptor for the fluorescence rather than a dynamic quencher, and then we have a dynamic quencher. And there's always, for all fluorophores, there you have to imagine in your head, there's a sphere of interactions around the fluorophore, and if there's a quencher within that sphere of interactions, the probability of quenching is 100%. So we can find that for a case of NADA, the neutral derivative tryptophan, quenched by acrylamide. You can have a upward curve which you could analyze in terms of the static and dynamic quenching, but there's another way to analyze it, which is, in molecular terms, is more correct, which is a quenching equation that accounts for a fluorophore having a quencher within its sphere of action where there's a high probability of quenching. So we've done that for tryptophan and acrylamide, and there's a derivation to this. It's a little hard to understand, but I'll just try to do this quickly to let you know it's not something we just made up. So this is the quenching equation we just presented in the previous slide. This is the dynamic part of the equation, and this is the part of the equation which deals for the fluorophores that are immediately quenched by molecules, by a quencher molecule within the sphere of action. So you can use Poisson statistics, and we naturally can't go through all of that, but we can say at a given concentration, there's a probability of so many N quencher molecules within the sphere of action. And there's also a probability, if the quencher concentration is low, that there are no quenchers within this sphere. So that would be the probability of no quenchers. And these are the molecules that you can observe. So the molecules that you can observe are decreased by all of those molecules that are immediately surrounded by a quencher molecule, and hence the upward curvature. Everything we described today, this is really a phenomenological description of quenching. We really haven't gotten into the mechanisms of quenching. And what reminded me of that is there are multiple theories for these sort of near field effects of immediate quenching, and they can be seen in viscous and non-viscous solution. But I don't think we'll discuss those in this course. So that's everything for the end of part A. For quenching, we covered static and dynamic quenching and tried to explain the phenomena in good detail. And in the next lecture, we'll look at other types of quenching. Thank you all for your attention.